Okay, last week we introduced chemical potential as a measure of whether or not reactions would take place. We introduced free energy of a phase as the sum over all I of the mole fractions of the individual components times their chemical potentials. And then we broke the free energy down into enthalpy, entropy, and volume terms, and then we calculated the conditions of equilibrium, the PT lines, for a number of simple reactions involving single component phases. So for single component phases, xi equals 1 is just one of them. So the free energy of the phase is equal to mu I and vice versa. So in the exercise you were given several reactions to calculate, and one of them was the aluminosilicate phase diagram. So the Al2SO5 phase diagram, and I thought it'd be good to just go over that. And we're using the condition delta G equals delta H 1 bar and T minus T delta S at 1 bar and T plus P minus 1 into delta V. So they're all solids, there are no liquids or gases involved, so we can assume that delta H and delta S are independent of temperature. We assume delta V is independent of pressure. Okay, and what I gave you were that for the reactions andalusite goes to sillimanite, if you want to put the component Al2SO5 andalusite goes to Al2SO5 sillimanite. And for that, we had a delta H 1 and T equals to 3054 joules. Delta S 2.97 joules per degree. And delta V minus 0.163 joules per bar. And andalusite goes to kyanite. Delta H is equal to minus 4352. Delta S minus 9.37 joules per K. And delta V minus 0.744 joules per bar. On the sheet I gave these in centimetre cube, but you have to divide by 10 to convert to joules per bar. So what the first thing we need to do is we need to get the third reaction, which is kyanite goes to sillimanite. And that's easy. We use Hess's law. We subtract this reaction from that one, and you can pretty easily see the andalucites cancel. Sillimanite remains on the product side. That is now negative, so it goes on the reactant side. So delta H for that reaction is equal to that minus that, which is minus 7,408, I think. 6, yeah. We do the same, we use Hess's law to get delta S. So it's this one minus that one. So it's 2.97 minus 9.37, which is 12.34. And thirdly, then we take this one from that one. So it's minus 0.163 plus 0.744. Somebody do that. Do it in your head.
Something wrong.
Hmm?
Something went wrong with the delta H and delta S. You subtracted the.
Did I do it wrong?
Well, for delta H, you subtracted 3,054 from.
7,000
And for the delta S, you did the other way around.
minus minus. That's right.
No, they did subtract the.
Sorry, 7406 has got to be plus. Sorry. You're right. That's right. Is that what you meant?
Yeah, there was
Yeah.
something wrong.
And delta V is 0.581. So it's minus that plus that. So it's 0.581. Okay, so to get the phase diagram, we do it on this side. So bring this down slightly. Sorry about that, it's difficult to get this exactly in the right spot. So we calculate at 1 bar. So of course at 1 bar the delta V term goes. We use T equals delta H over delta S. So as a first reaction, andalusite sillimanite. The temperature is equal to, I'm not going to do that in my head, I'm going to check it again. Seems like I get a different answer every time I do it. 3054 divide 2.97, 1028. Didn't I get 1043 before?
Yeah.
Oh, obviously I was wrong. Did I write it down wrong? Yeah. So it's 1028 at 1 bar, and dt dp is equal to delta V over delta S, which is minus 0.163 over 2.97. trying to do this correctly this time. 0.163 divide 2.97 minus 0.05488. Add lucite kyanite. T at 1 bar is equal to minus 4352 divide 9.37 464 and the TDP is 0.744 9.37 plus 0.079. 4 is the third figure. Haven't written it down. Got your calculator, could you check that for me? Kyanite, limonite.
That's correct.
T at 1 bar is 7406
600.
12.34 600. Thank you. And the TDP is equal to 0.581.
0.047.
Oh, got it wrong. Okay. Sounds right. 0.047, you say. 0.581 divide 12.334.
Yep.
0.047. Right. Okay, so now we can, I think, rub out this lot. It is working, I think. So we can start sketching a phase diagram. So at 1 bar, we have 3 reactions. One is at 464, second one at 600, and the third one at 1028. And this one has a negative slope. And these two, this has a steeper positive slope than that one. Is that right? Yeah. So that looks like that. That looks like that. So, so far we're doing okay. we take the andalusite-slimonite reaction. It has a positive delta S and a negative delta V. So we know that slimonite is stable on the high temperature side. So that's slimonite and that's andalusite. The andalusite kyanite is the lowest temperature one. That has delta S is negative and delta V is negative. So the kyanite has got the lower volume and the lower entropy, so it's on the high pressure side. Okay, so delta V for that one is minus 0.744 joules per bar. So kyanite, which is the product, is a lower volume, so kyanite is here and andalusite is there. And if we take the third one, kyanite-slimonite, that also has, which was the one we calculated, delta V is plus 0.581 joules per bar, which means that the products, the slimonite, have got the higher volume, so that's the low pressure side. So slimonite is there, kyanite is there. Alright, well so far it doesn't really look like the diagram we're all familiar with, so let's continue these lines until they intersect. Change the slope on the other one slightly. So it's still not quite looking the way we expect. This is the andalusite-slimonite reaction. So we just continue these up on the other side of the invariant point, which is there. So that's kyanite-slimonite. And this is kyanite-andalusite. So the important point is that some parts of these reactions are stable and some parts are not stable. They are metastable. That is, they are a stable assemblage, but one of the other phases is even more stable. So let's look at this here. This is a reaction kyanite goes to slimonite. However, everywhere to the left of the andalusite-slimonite line, andalusite is more stable than slimonite. And everywhere to the right of the kyanite-andalusite reaction, andalusite is more stable than kyanite. So this reaction is not a stable reaction, it's metastable. Okay? So if we were to put kyanite and slimonite together, there say, they would be stable together. But if we introduce andalusite, that would become even more. That would be even more stable. So that is that's a metastable reaction. Let's look at this one. So everywhere to the right of this line, of that line there, slimonite is more stable than kyanite. And everywhere to the high pressure side of this line, slimonite is more stable than andalusite. So that reaction is metastable in that region. And by the same arguments, the slimonite-andalusite reaction is metastable up there because kyanite is more stable. Okay, so now we can ink in the stable reactions clearly, and that now looks much more like the phase diagram we used to. Okay, all the reactions are equilibrium lines all the way out to infinity, infinite pressure, if you like. That's the equilibrium line, but they are less stable. Those two minerals are less stable than other minerals in these fields. So this is the field of kyanite, this is the field of slimonite, and this is the field of andalusite. All right, the other thing we can do is we can calculate the triple point from any two of these reactions. So we take the first one, andalusite slimonite, T equals 1028 minus 0.05488 P. Strictly should be P minus 1, but P is going to be so big relative to 1. We won't worry about it. And then for the second reaction, andalusite kyanite, T, sorry, let's write that, andalusite kyanite, T is 464 plus 0.0794 P. So there we go, simultaneous equations, we can solve them. If we subtract this one from that one, we'll get 0 equals 564 minus, do this in your head for me, not 13,
I can't actually see.
sorry, 1382 is it?
Let's see. What have you done? Like 1328.
428. 13. Call it 1343. P. So P equals 564 over 0.1343. Five six four divide 0.1343. That does not look right. Oh, it does. That's right. 4,200. 4,200 bars. And T is going to equal let's just take the second one, plus 0.0794 times 4,200. .464 plus 797. So that is 4,200 bars, 0.797 K, which I seem to remember is about right, so that's good. Okay, so up to now we've been talking about reactions involving solids only. Well, what about gases? Reactions involving gases or fluids are really important in our sciences. Obviously, we can think of reactions in solution at low pressures and temperatures, but there are also reactions involving gases such as water and carbon dioxide at high pressures and temperatures, which are important in metamorphism. So let's think about a reaction involving a gas, and I've got some data here for this reaction, and that is the reaction of calcium carbonate with silica. Make that calcite plus quartz. And in metamorphosed limestones, impure limestones with some quartz in them, these will react to make a calcium silicate. And evolve carbon dioxide. So this is not a pyroxene, it looks like one, but it's what's called a pyroxenoid. It has a different structure, and it's called elastomite. Not uncommon in metamorphosed limestones, skarns. And I've got some data for this reaction. I think, yes I do. So delta H at 1 bar and T is 79,200 joules. Delta S is 146.9 joules per K. And so what happens now, as we can calculate the equilibrium temperature at 1 bar. So T at 1 bar is delta H over delta S, which is 79,200 divide 146.9, 539 degrees K. Okay, now to go to higher pressure, we use delta G0 at P and T is delta H at 1 bar and T minus T delta S at 1 bar and T plus the integral from 1 to P of delta V to P. Now, when we were talking about solids only, we assumed that delta V was independent of pressure. It was a constant. Okay? However, this reaction involves a gas, and gases are definitely not incompressible. As we go up pressure, they definitely their volume definitely lowers. Carbon dioxide, for example, which would have a volume per mole of 22 litres at room temperature and pressure, can easily be turned into liquid carbon dioxide under pressure. It liquefies and its volume goes down dramatically. So in the case of a gas, delta V is not constant. Gas is compressible. So we want to calculate this reaction at higher pressures. We need to do something about that. So what we need to know, how does the volume of carbon dioxide vary with pressure? And in order to figure that out, we need what is known as an equation of state. An equation of state is a very simple equation that connects volume to pressure and temperature. Okay, so we need an equation of state. So V as a function of pressure and temperature. All right, someone give me an equation of state for a gas.
PV equals nRT.
Yeah, PV equals nRT. That is the equation of state for a perfect gas. Sometimes called an ideal gas. That is a gas, a theoretical gas, in which the molecules, all interactions between the molecules are perfectly elastic collisions, in which there are no forces between the molecules, and the molecules are infinitely small, etc., etc. N is the number of molecules. Or number of moles. R is the gas constant. Which is 8.314 joules per degree per mole. Okay, so we just consider 1 mole of gas. So N equals 1, PV equals RT. So we'll use that as a starting point. Okay, so delta G is going delta H at 1 and T minus T to delta S, 1 and T. Now what I'm going to do is I'm going to take delta V and I'm going to separate the volume of CO2 from the volumes of the solids. Okay? So that will be then plus the integral from 1 to P of V CO2 dP, that's a product, so it's positive, plus the integral from 1 to P of delta V of the solids. So the solids would be the volume of wollastonite minus the volume of quartz minus the volume of calcite. So that's the volume of wollastonite minus the volume of quartz minus the volume of calcite. Okay, so what I'm going to do is I'm going to say, let's assume that for the solids, delta V of the solids that's independent of pressure. That's essentially a solid-solid reaction, so delta V can be taken to be a constant. And now I'm going to substitute my equation of state for CO2 in there, for volume there. Let's just write that out. So delta G at 1 and T, sorry, delta G at P and T plus P minus 1 into delta V solids plus the integral from 1 to P of V CO2 dP. And I'm going to make the substitution, assuming a perfect gas. CO2 is about as far from being a perfect gas as you can get, actually, because it liquefies very easily and there's strong forces between the molecules. But we'll start off with this assumption just to see what happens. So we'll assume PV equals RT. So the volume of CO2 is RT over P. So this then is delta G plus the integral from 1 to P of RT over P. Okay, so this term we can take the RT outside, they're constant. We're doing this at constant temperature, T. And so the integral of 1 over P dP between 1 and P, integral of 1 over dP over P is ln of P. RT ln of P minus RT ln of 1 for the lower limit of the integral, and of course ln of 1 is 0, so that's 0. So putting some numbers in here, delta V of solids is, I have written down, minus 1.969 joules per bar. So delta G, P and T, and we want to set that to 0 to calculate the equilibrium conditions. That's going to equal 79,200 there, minus T into 146.9 plus P, we'll ignore the 1, so P into minus 1.969. Okay, it's there, P minus 1 if you prefer, but not worth worrying about. And plus RT ln of P. So rearrange that, bring the T terms on this side, so T into 146.9 minus R ln P equals 75,200 plus P into minus 1.969, or T equals 79,200 minus 1.969 P over 146.9 minus R ln P, where R, if you remember, is 8.314. So that's assuming that the carbon dioxide behaves as a perfect gas. Actually, I'll put it onto this board. How are we doing? Bags of time. So we have that T is 79,200 minus 1.969 P over 146.9 minus R ln P. So if we draw our PT diagram, at 1 bar we calculated was 539. Delta S is positive, so let's bring this back again for a second. Delta S is positive, which means that the products are the high temperature side, which is logical and obvious because as you heat things up, you'll degas them. Okay, it's like boiling water. So this is the high temperature side. All right. So why don't we do the calculation? Let P equal 500 bars. Let's see what we get. So we let P equals 500. And let's do it at P equals 1,000. Just to show what happens. So 500 bars. Put in, so that's 79200 minus 821. You get that? Eight, 2, 1. So this is 500, 6, 7, 8. So that's 8. You got 480. Well done. So that's 500. So that's 821. And if I put in 1,000, I'll get a temperature of 79,200. I hope this is visible. Actually, I can check. It is, right. $863. And if you put in 2,000, you get P equals 899. So if that's 500 and 1,000 is about there, it goes up like so. Sorry. I guess 1,000 might be a little. Anyway, the point is it's very strongly curved. So 2,000 is up here. 899. So unlike the case of our solid-solid reaction, which is a straight line on a PT diagram, this one is strongly curved. And it's strongly curved because the carbon dioxide compresses as you go up pressure. So delta V is changing, and so dt dp is delta V over delta S, and delta V is getting smaller and smaller, so dt dp is getting smaller and smaller. But delta S isn't changing very much. That's why you get this strong curvature. And so this is calcite plus quartz, and this is wollastonite plus CO2. Okay, so I hope that's reasonably clear. Now the whole point here is that CO2 is not a perfect gas, and neither is water, and both of them are quite a lot different from perfect gases. And so what do we do in the case of it not being a perfect gas? Because it's not a perfect gas, it doesn't obey PV equals RT. PV is something different. Close, but no banana. It's not quite close enough. So what we do in the cases of an imperfect gases, PV is not equal to RT, but we introduce a thing called the fugacity coefficient. So that RT LMP is replaced by RT LMF. So F is equal to P times some coefficient, which we call gamma. And this is the fugacity coefficient. So for a perfect, what's the fugacity coefficient of a perfect gas? 1, exactly. So for a perfect gas, capital gamma is 1. Real values for things like water and CO2. So capital gamma for CO2, I have a value here. It's about 2 kilobars. About 2,000 bars. So what do you do where do you get these fugacity coefficients from? So if we introduce a fugacity coefficient for CO2, that is going to, what does it do at 2,000 bars? It will shift the temperature from 899. Not sure how much difference it makes, we'll try it. 79200 minus. It shifts it to 965. So that 899 becomes 965 K. And basically what's happening is we're destabilizing the carbon dioxide side of the reaction. We're making the low temperature side more stable and destabilizing the carbon dioxide side because its volume is higher than a perfect gas at the same pressure. Okay? So where do we get these values from? Well, actually, they just have to be measured. The best values for water, at least, have been measured by geologists. And the equation of state of water to 10 kilobars and 1,000 degrees was measured about just over 50 years ago at Penn State University, and it was a group led by a guy called Wayne Burnham. And Wayne Burnham was a little bear of a man, but before the Second World War, he'd been a machinist who worked in a machine shop, and so he knew a lot about the technical work of how to make things. During the Second World War, he was a US Navy pilot, and he was on an aircraft carrier that was sunk at the Battle of Iwo Jima, and spent 2 years in hospital after that recovering. And after the war, he went to university and he studied geology. And then he worked on skarns and granites, and he really wanted to figure out how granites worked. What was the granite system? And he realized that in order to understand granites, because granites are wet, he had to understand water. So he spent the best part of 10 years measuring the equation of state of water. He designed the bellows, he built the pressure vessel, the whole thing. And at the end of that, they published a monograph, which is an absolutely classic study of how to measure the equation of state of a gas. It's just brilliant. The apparatus was brilliant. A little bellows, it expanded and contracted as they changed the temperature. And they measured that with a capacitor. And at the end of all that, he published this, and he was invited by the International Union of Pure and Applied Chemistry. He was invited to join their commission on the properties of water, having done the best study ever on the PVT, equation of state of water, and he refused. And I asked him once, he's dead now, but I asked him, why do you refuse, Wayne? And he said, I wasn't interested in water, I was interested in granites. But I realised that in order to understand granites, I had to know water, so I mentioned water. There you go. All right, I'll do.